Okay, well, thank you, Christelle, for the very nice introduction, and thank you to all of the organizers for having me. Yeah, I think it's really nice to be able to come together as a math community, even though we're all stuck in our own homes. And I really appreciate Andrew's introduction that he gave at the start of his talk, calling for us to examine our own biases and what we can do to support our Black colleagues. And also, before starting my talk, I'd like to acknowledge that I live and work on the traditional territories of the Duwamish and the Coast Salish peoples, even though, well, right now I'm living and working in the same place, but normally also the University of Washington is also on traditional territories of the Duwamish and Coast Salish people. So let's get started. So everything I'm going to say today is joint work with Abby Bourdon, Özlem Eder, Yuan Liu, and Francis Odumodu. I think Abby and Özlem are in the audience. And our initials, if you put them in alphabetical order, spell out Belov, so all of our results will be denoted by that. This is not another mathematician, it's just our name. Okay, so let me first start by talking about just points on curves. And I'll begin with a theorem that was recently featured on the My Favorite Theorem podcast. Was Ruthie Horch's favorite theorem at the beginning of April. And I think it's probably many of our favorite theorems too. So you take a nice algebraic curve over the rational numbers, and then Falting's theorem tells us that the curve C has infinitely many rational points only if the genus is at most 1. And this is sort of a prototypical example of a result where showing how geometry controls arithmetic. So in this case, our geometric property, is the genus. So the genus we can read off just by looking at the curve over C or over an algebraically closed field. And then that's telling us about the arithmetic properties of the existence of rational points on C. And so if the genus is too large, then we can never have infinitely many rational points. Okay, and this theorem is even better than what I stated on the first slide. It's not just true for curves over Q, it's also true for curves over any number field. So if you have, in particular, if you have a curve over Q and you make any finite extension, you still always, you can never cross that barrier to having infinitely many points if your genus is too large. Okay, so I'm going to use this as a starting point. So I want to just rephrase a few things. So what do I mean when I'm talking about having infinitely many k points? So I like to think sort of very explicitly. So if you imagine your curve just cut out by a bunch of equations, then we look at all of the solutions over the algebraic closure, and the k points are exactly the ones where we can write it in some list of coordinates where all of those coordinates are in the field C of k that we care about. So I'm just going to now write the set C of k being infinite. That's our set of k rational points. And I'm also going to work with just curves over Q, but then think about points of them over extensions. And this is just for simplicity. Just so that there's not too many different fields floating around with names. My base field of the curve will always be Q. Okay, and then another, so this way is sort of like concrete equations way, but we can think about it in a, I don't know, more schemy way if we want. We can just take any point on the curve, and then we want the residue field of this point to be a number field k. And then when you write it this way, you see, well, when you consider the whole set of things, there's no additional structure that you need because you're working with a field k. Oh, move to laser pen. So, you know, I need to be working over a field so that I can make sense of plugging in things to these equations. So I can add and multiply and do arithmetic operations with the coordinates of the field. But then once I have this point, there's nothing that's happening, no arithmetic or algebra that's happening among the different points in this set. So then when you see that, I think you're led to the question, okay, well, what if I don't care about it being a particular field, but just a field of a particular type? So maybe I bound the degree of the field. So for instance, I want to look at points that are defined over a quadratic extension, but I don't care about which particular quadratic extension I care about. And so this is a perfectly nice class of points on the curve. And this is called the set of degree d points on the curve. So this is just the set of points on the curve where the residue field gives you an extension of degree at most d. Oh, sorry. Okay, I guess technically, since I said degree d points, this should really be inequality. Okay. So I would like to ask what the analog, or whether there is an analog of Falting's theorem, if instead of caring about the set of k rational points, we can care about the set of points of degree d. And so the set of degree d points is different than the set of points over a number field. So probably we don't have exactly the same condition, but we have some condition that we can hope will go in there. So maybe another way to say this is that I'm interested in what geometry of the curve is controlling these arithmetic properties of having infinitely many degree d points on the curve. Okay, so let's start by looking at this in an example. Okay, and for a simple example, I'll take a double cover of P1. So I'll look at a curve whose open subset is cut out by this equation, y squared equals x times x minus 1 times x minus 2, x minus 3, x minus 4, x minus 5. I can think of this as a double cover of P1 branched over the points 0, 1, 2, 3, 4, 5. And this, by Riemann-Hurwitz, is a genus 2 curve. And we know, so then we know by Falting's theorem that this curve has finitely many rational points. And better than that, not just it has finitely many rational points, but for any finite extension you make, so over any number field, this curve still has only finitely many points. But if you look at this equation, you see that if you plug in a rational number for x and then solve for y, you're going to get a quadratic point. You're going to get a point of degree at most d. So for all of the infinitely many choices of x that are rational numbers, you're going to get a point that gives you a degree at most 2 extension of the rational numbers. And so in particular, we get infinitely many degree 2 points. Sorry, I was just looking at the Q&A, but I think maybe I'm not supposed to pay attention to this. And even more than that, you can expand this example to add more and more branch points, however many branch points you want, to create a curve of genus as arbitrarily high as you want, and the same argument / construction still holds. So for every one of the infinitely many rational numbers x, I plug them in, and solving for y gives me at most a degree 2 extension. So we see that this question of having infinitely many degree d points, already when we go to d equals 2, which is the first case when it's different than what we were studying before, we know that just looking at the genus of the curve is not enough. The geometric invariant of the genus is not enough to control this arithmetic property. We need something stronger, a finer invariant. Okay, and just to go through some of these things more, let me just explain pictorially what's happening. So this curve on top, all the black bubbles is my curve C, and this curve on the bottom, oh, that didn't work very well, but this curve on the bottom is acting as P1. And so what is happening? What is the geometric version of the argument that I had? Well, on P1, there are infinitely many rational points. Okay, I didn't exactly draw infinite, but hopefully it makes you think a lot. And for each one of those rational points, so for instance, if I start, so there's some special ones. Those are the branch points. So here I've made all of the branch points rational. That's not really necessary. But aside from these pink dots, above some rational point here, the points lying above it may not be defined over the rational numbers, but they must be Galois conjugate, because this whole picture is defined over Q. And so Galois has to send this point to another point that maps to the same rational point downstairs. So those are Galois conjugate, and in fact that will happen for all of the rational points and all of the black circles. And in fact, above the rational points downstairs, there's a delay. You guys can't really see my laser pointer before it disappears. Okay, so I will write. So on the rational points downstairs that have no black circles above it, what is happening? Well, the quadratic points are still there, but they're just giving me imaginary quadratic fields rather than real quadratic fields. So the blue ones are representing points defined over imaginary quadratic fields, and the green are over real quadratic fields. Okay, and it can happen for some special selection of these points that these points actually turned out to be rational. But because we have genus at least 2, that can, and we have Falting's theorem, that can only happen for finitely many of these curves. So finitely many of these points are actually rational, and then all of the other x's you should think of as not living in the rational numbers, and you actually need to take an extension. Okay, and so this is exactly what's happening here. It is the rational points, the infinitely many rational points on P1 that are leading to our infinitely many quadratic points on this double cover. Okay, so this is, I think you can imagine that this picture generalizes to d greater than 2. And so we're going to use this to make a definition. So if you have a nice algebraic curve over Q, then I'm going to say that a degree d point is P1 parametrized, so same one of these, if there is a degree d map. So this, in this case, this is a degree 2 map, and these are degree 2 points, such that this point maps to a rational point on the base. So the really important piece is that the degree of the point is the same as the degree of the map. And then the image becomes rational. Okay, so that's what it means to be P1 parametrized. And if you can't do this, if there is no such map of the same degree of the point, then we say that the point is P1 isolated. Okay, so this picture shows you that all of the points that are x's, those are all P1 parametrized, because if the line is connecting just 2 x's, those are degree 2 points. This is a degree 2 map, and they're all mapping to these green dashes, which I said were rational points. And then it takes more work, but you can show that the dots are all P1 isolated. So the dots are degree 1 points. So to show that they're P1 isolated, I have to prove that there are no possible degree 1 maps from the curve to P1. And in this case, now I can use the geometric invariant, the genus. For a genus greater than 0 curve, there's no degree 1 map to P1. So that tells me, that completes the argument to show that these are P1 isolated. Okay, so this happens a lot in math. You ask when you can have infinitely many points. You find an example, you sort of systematize the example, put it in a classification, and then you ask, okay, is that the only way that I can get infinitely many rational points? So we can ask ourselves, oh, this is just what I said. So that if you have this degree D map, then you do get infinitely many degree D P1 parametrized points just by taking pre-images. So this, having this map gives you, we know once you have one P1 parameterized point, then you have a map like this, and so then you get infinitely many parameterized points. So then can we ask ourselves, are maps to P1 or degree D maps to P1 the only way that we can get infinitely many degree D points? And if you think about the argument that we went through, the main thing that we used was that the base curve has infinitely many rational points. And then if you remember all the back to the beginning, Faulting's theorem told us that the only way that we could have infinitely many rational points was if we had a curve of genus 0, which is P1, or if we had a curve of genus 1. So there's one extra case that we could have of curves that have infinitely many rational points. And so you could run the same construction that I explained by replacing this P1. Instead, we have a genus 1 curve with infinitely many rational points. So if you had a map like this, this would also give you a construction. Okay, so I'm going to make a definition, and this one is really a definition star. So right now, this is just a flavor of a definition, that you have a degree D point, and we say that it's AV parametrized, so AV for abelian variety, if X is parametrized by a positive rank abelian variety. Okay, what does it mean for a point to be parametrized by a positive rank abelian variety? Well, one example is that you have a picture like I have below, where this is a positive rank elliptic curve. But unlike in the case of P1, this is not the only way that you could have a family parametrized by abelian varieties. So this is the precise definition. I'm just going to leave it up here. You can read it if you want. So there's a few extra things you have to take into account. One way to think about it is basically you can have infinitely many degree D points coming from correspondences given by positive rank abelian varieties rather than just a map to a positive rank abelian variety. So it's a little bit more complicated, but it is a precise definition that we understand. And the picture on the bottom of the slide is an example of being parametrized, being AV parametrized when this curve is a positive rank elliptic curve. And you'll be fine if that's the picture you keep in mind for the rest of the talk. Okay. And then I'm just going to say that a point is parametrized if it's parametrized by a P1 or an abelian variety. So I don't care what kind of variety it's parametrized by, but just that it is parametrized. And then I'll say that it's isolated if it can't be parametrized by either. So then it's P1 and AV isolated. So parametrized and isolated are exact opposites. Okay, so how should we think about these points? Well, parametrized points you should think of as the ones that are better understood. So we can understand them through these other constructions. They relate They sort of, in some sense, come from either a P1 or positive rank abelian varieties, which we have, well, P1 we understand really well, but positive rank abelian varieties, there's been a lot of work to understand them. Oh, I see somebody asked, what is WD of C? So that is the, well, I guess conventional notation for the image of, let me just go back. I'll write it down. So this is the image of, you look on sim D of C, so you take unordered points, collections of D points, and you map to pick D of C. So, so you basically just take a collection of D points and then you send it to its divisor class, and WG is the image of that. And so if that didn't mean anything to you, don't worry, it's not necessary for the rest of the talk. Okay, so these parametrized points, they're, we just have other ways to get at them. And yes, understanding positive rank abelian varieties is difficult, but that's something that we have been studying a lot. And even though we can't always prove what the answer is, we've developed a lot of, we're sort of get to leverage a lot of advances in studying that question to understand parametrized points on these curves. So then what's going on with isolated points? Well, I think we don't have a very good idea of what's going on. So there are a few things we can say. So you can prove that there are only finitely many of them on any curve. So overall, infinitely many points on the curve, infinitely many algebraic points, only finitely many of them are isolated. So the vast majority of points on the curve are parametrized, usually by P1, but also by abelian varieties, positive rank abelian varieties. And I think if you made people guess, I guess we could try to take a survey of the panelists, but sort of going from folklore suggestions and just thinking that sort of rational points don't want to exist. I think the guess would be that for some definition of most curves don't have any isolated points. So this is very big, but sort of how you should think about them heuristically. But I think these two things together show, so there's a finite collection of all the infinitely many algebraic points, and probably there's not a good reason for them to exist. So I think it's fair to call them mysterious points. Just return to my who knows emoji about these isolated points. Okay, and why do we care about the distinction between being parametrized and isolated? Well, this is exactly what we need to answer the question from the very beginning. So what is the analog of Falting's 83 theorem, where instead of studying infinitely many points over some number field, we study infinitely many degree D points. And the condition, which follows from a later theorem of Falting's, but you just have to do sort of a little bit extra work to pull this out, which is in our paper, that you have infinitely many degree D points if and only if you have a degree D point that's P1 or AV parametrized.
Bianca, we have a Q&A asking if there's a link between your guess and AV parameterized points and questions of Andre Oort type.
I think, well, I think there's definitely a philosophical connection, which is that we don't think you should have lots of things occurring unless there's a good reason for it. But I think beyond that, I can't answer off the top of my head. I think it would be interesting to think about, but yeah, for me to say anything, I don't know, valuable, I think I would need more time. So I'll just leave it at the philosophical link being clear, and yeah, maybe there's a more concrete link to explore. That would be interesting.
Thanks.
Okay, and just to compare, so Falting's theorem, 83 theorem that I mentioned, I emphasize the point that we should think about this as an example of showing how geometry controls arithmetic. And here you can argue correctly that having a degree D point that's P1 or AB parametrized is not a completely geometric property, because well, for a P1 parametrized, you need this map defined over the rational numbers, and for AB parametrized, we talked about a positive rank abelian of variety, which is a very arithmetic content. Using the geometric shadows that parametrized points cast, so this was explored by Abramovich and Harris and Fry, and then there's related work very recently by Smith and Vogt. So you can make this a geometric only if statement, which very much mimics the original Falting's 83 theorem when you replace this boxed condition by something weaker but more geometric. So this really is giving us the analog. Okay, and yeah, this is just the same phrasing, but writing the contrapositive, maybe, so that you have finitely many degree D points if and only if every one of your degree D points is isolated. And I think that this is probably the strongest statement that you could make without any assumptions on the curve. So that if you just, because just like you can rig a curve to have some number of rational points, you should also be able to rig a curve to have some number of isolated points. And so I don't think there's something better, much stronger than this, that you could say in general. But there are a lot of curves that merit much more attention than others. And one of those classes of curves that we turn our attention to was focusing on curves that are themselves moduli spaces. And why would we want to focus on these curves? Well, if we understand the arithmetic of these moduli spaces, which in the case that those are curves, then that tells us something about the arithmetic of the objects that these moduli spaces are parametrizing. So we sort of get more information almost for free by the amazingness of moduli spaces. Yes, nice is smooth, projective, and geometrically integral. There's a question from the QA. Oh, yeah, so someone else asked if the guess is most curves don't have any isolated points. Is there a simple example of a curve with an isolated point? And yes, so if you have a curve of genus at least 2, then every rational point is isolated. So we have examples of curves with rational, finitely many, but non-zero number of rational points. So that gives examples. There are recently some further examples of isolated quadratic points. So I think maybe this was first done in a paper of Samir Siksek when he was developing techniques for using Chabuchi on symmetric powers of curves. And then recently that work has been taken up. So there's a paper of Aiken Osman and Samir Siksek, where they're studying quadratic points on certain modular curves. And then sort of when you study the curve afterwards, you can see that some of these quadratic points are isolated. And also there is a paper of Jackson Morrow and Joseph. I'm really sorry, I'm blanking on the last name. If anybody is here and wants to post the last name into the Q&A, I can picture his face, but I can't, yeah, just having a brain freeze.
Gunther, someone is addicted.
Thank you. That's it. Joseph Gunther and Jackson Morrow. So they have a recent paper that studies quadratic points on curves and then also gives some examples. Great. Okay, so and what is one extra piece of information that we could use when we're studying moduli spaces to try to get more of a handle on isolated points? Well, moduli spaces, there's often ways of refining them. And so then you don't they don't come kind of one at a time, but they come in a collection and are organized in a tower. So as I'm drawing here, and you should think of this as going sort of infinitely far and infinitely high up. And if I was giving this in person, I would point all the way up to the ceiling. So I just encourage you to think of these curves dancing up your wall, going all the way over and all the way up. Okay, so when you have a tower, so the building block of a tower is a morphism. I mean, that's the extra piece of information you have than the curve standing alone. So the first question that I looked at with my co-authors is how isolated points behave along morphisms. And what we prove is that if you have a point that satisfies this genericity condition, so that the degree of the point you start with is as big as it possibly can be, given the degree of the map and the degree of its image. So this is a genericity condition that holds for a lot of points. But if you have a point like this, then being isolated pushes down across the morphism. So if you're P1 isolated on C and you have this genericity condition, then you will be P1 isolated when you map. Your image will also be P1 isolated, and the same for being AV isolated. Okay, so as long as you satisfy this genericity condition, then isolated points push down along morphisms. Okay, so how can we think about this in a tower? Well, remember we have this tower going infinitely high up where the curves are going all the way up your wall to the ceiling and up into the sky. And what this tells us is that if you have an isolated point high up in your tower, if it's generic with respect to that morphism, then it should push farther down in the tower and should be able to be detected. Well, the hope is that you would be able to detect it low down in the tower. So that's sort of the slogan of this theorem, that if you have isolated points somewhere in your tower, you probably can detect them fairly low in the tower. But again, this is can likely be detected because this depends on this genericity condition. So let me just say, so what we did is we explored the tower of modular curves x1 of n. And let me just remind you, so non-cuspidal points on x1 of n correspond to isomorphism classes of pairs, where it's elliptic curve comma point, and the point is a point of order n on E. So if we understand things about isolated points on x1 of n, then we will understand things about the arithmetic of torsion points on elliptic curves. And for those of you who are elliptic curve fans like I am, you hear something like this and you go, wait, don't we know everything there is to know about torsion on elliptic curves? And the reason we think that is because we have this extremely strong, super amazing theorem by Morel that tells us a lot about torsion on elliptic curves. So what it says is that if you fix a positive integer d, then there's a constant depending only on that positive integer, such that for all number fields k of degree d and all elliptic curves over those number fields, then the size of the torsion on the elliptic curve over this number field is bounded by this constant. that depends only on the degree of the number field. This is a super amazing theorem. It's what all boundedness theorems in number theory want to be. And if we phrase it, in terms of what are isolated points on the tower, then what it tells us is that if you have an isolated point on x1 of n for n sufficiently large, so high up in the tower, then it tells us, well, then the degree of that isolated point is going to be pretty big. And what this means is that isolated points in the tower should be hard to find. Then we don't have as many feasible computational tools to get a hold of them. So Morel's theorem, like as amazing as it is, it tells us actually, what it tells us about isolated points is that they are hard to find. Maybe it gives more evidence that they are mysterious and confusing. But our theorem sort of does the opposite thing, the complementary thing to Morel, is it takes these isolated points high up in the tower and it says, okay, maybe they're hard to find high up in the tower, but let's not worry about finding them high up in the tower. Let's push them down and see if we can detect them low down in the tower. So we looked at this for this family, x1 of n, and what we proved is that if you chop off the tower horizontally, so now it's finite width, but still goes infinitely high up. So still going all the way up to the sky. And if you look and you try to understand non-CM, and I should have put non-cuspidal isolated points on these curves that correspond to elliptic curves over Q. So not all isolated points, but isolated points that when you map them all the way down to the J line, map to a rational point. And so what we prove is that those isolated points, there is some line that you can always detect them below. And we give sort of an explicit description of what this line is based on, you have to, so the description is given in terms of certain Galois representations on elliptic curves. So it's not, I can't tell you it's below like 42. One, that's too small, and also that's not the way that our formula works. And I will just end with saying that if you dislike the finite width part, sort of, conjectures, maybe folklore strengthening of conjecture, suggests that we should be able to remove the restriction, but we can't remove it unconditionally. And I will end there. Thank you for your attention.
Thank you, Bianca.